Hello everyone, welcome back to Electronics 1. We're continuing on at lecture 9 today. Last lecture we looked at a variety of different configurations of op amps that allow them to be used in different applications, filters, high and low pass filters, summers, integrators. Today we want to go back and address one of the properties of an op amp that relates back to our amplifier models that we looked at in one of the earlier lectures, and those parameters are input resistance and output resistance. So let's start by looking at input resistance. Okay, so input resistance can be assessed very simply by using Ohm's law and a test voltage. So if I take just treat this as a black box here, I guess in this case a white box, but this box has some network in it, and without knowing the details of that network, I can assess the input resistance, so the resistance looking into the input, by simply applying a test voltage. So if I connect a test voltage, let's call it Vx, to that input, and based on the amount of current that's flowing into that input, I can calculate the input resistance. It's simple Ohm's law, right? The input resistance is going to be equal to the voltage that's applied to that input divided by the current that's flowing into that input. Okay, so seems simple enough. Let's apply that concept to the amplifier, a couple of the amplifier configurations we've been looking at for op amps. Let's start with the non-inverting configuration. So non-inverting amplifier, and let's look at its input resistance. Okay, so my non-inverting amplifier, hopefully you recall, is designed with my negative feedback going from output terminal to inverting terminal, as is always the case for our op amps when configured for as an amplifier. We need negative feedback to stabilize the gain. Okay, so again, if I think about this op amp, well, I can really think about it as a black box again, just like I did above for that network. Okay, so this being the input, and I can show the output here, although we're not particularly interested in the output at this point. So again, just like in my generic network above, I can assess the input resistance by applying a test voltage Vx to this input and measuring the amount of current that flows in this input. In this case, as we stated, one of the properties of an ideal op amp is that the input, the resistance looking into the input terminals is infinite, and therefore no current flows into those inputs. Therefore, simple Ohm's law will tell us that, well, if the current is 0, then any voltage divided by a current of 0 is going to give an input resistance of infinity, which coincides with what we've said about the input resistance of an op amp, and really we've kind of we've kind of worked backwards here, because we already said the reason that the put current as 0 is because the input resistance is infinity. But this analysis just shows that our technique for applying a test voltage, I guess, holds up. Okay, so let's look at this idea of this property of the input resistance of a non-inverting amplifier being infinite. So here we're not just looking at the op amp itself. We're looking at the op amp configured to have some gain that's equal to, as we know from previous lecture, the gain of this op amp is equal to 1 plus R2 over R1, right? So again, we've already accepted that the gain of an op amp by itself is very large, but here we've got it configured into a controlled configuration where we have the gain set to a very specific value that's going to be known and stable, and yet we still have an input resistance that's infinite. So this is quite an appealing property of this amplifier as we compare back to our amplifier models from the beginning of the term, where we said one of the ideal properties of a voltage amplifier is infinite input resistance. So we are still approximating that with our op amps. And again, we're still assuming our op amps are ideal, but in fact, even a real op amp has an input resistance that is often in the hundreds of mega ohms or even gigaohms. Okay, that said, to to show that an op amp is a very good approximation of an ideal amplifier. Even in the real sense of an op amp, it's still a very good voltage amplifier. Let's go back to something we talked about previously. We talked about a voltage divider and the output of that voltage divider. All right, so if I label the voltage at this point here, let's call this point A here maybe, and the voltage at this point, let's call the voltage here VA, and we said that the voltage at that point can be calculated just using our voltage divider rule, which is R2 over R1 plus R2 times the voltage that's applied to the pair of the resistors. Okay, but this is only true. Okay, so here's the important part. This is only true if Ix, which I haven't labeled here yet, if the current flowing from this center point of these op amps, center point of these resistors is 0. If there's any current flowing out from the middle of this voltage divider, then this formula does not hold, because my resistance ratio isn't truly what is represented just by these resistors. The current flowing here would imply that there is some additional parallel resistance in parallel with R2, right? If this current was some value, that suggests that there's some resistance in parallel with R2, so this equation here is again no longer true. So but how do we ensure that our current here is 0 while still making use of this voltage VA that comes from the center of these two resistors? Well, we just got done saying that by using an op amp here with its infinite input resistance is going to ensure that this current flow is 0 from the center point of this voltage divider. Okay, but you might say, well, maybe I don't want to put a gain on this this signal. Maybe I want this voltage VA. Well, by taking, here's a very special and useful configuration of an op-amp, by connecting the output directly back to the input, right? And if we think about this for just a second, we know that an op-amp, because of the op-amp itself having a gain that's very high or assumed to be infinite, that whatever voltage is at the one terminal also appears at the other terminal. So this voltage at this terminal is going to be the same as the voltage at this terminal, which was VA. And this voltage here, well, that voltage is tied directly to the output, so the output is also going to be VA. The beauty of all this is, though, now I can still tie a load to the output of this circuit, so I can put a resistor on here, let's call it RL, and this output voltage will be equal to the voltage VA, and I can supply current to this resistor, so this IL is can be some value, whatever it is, some value in amps, but yet does not impact the voltage divider at the input. So none of this back here is impacted because my op-amp is acting like a buffer. The op-amp is supplying the current here. This current IL is being supplied by the output of the op-amp and not being supplied from the center point of that resistive voltage divider. So this is known as a unity gain, unity meaning a gain of 1, or unity meaning 1. So we have a gain of 1 buffer. Buffer meaning a device able to isolate the input from the output. So we often talk about buffers when we want to increase the amount of current that a circuit is able to provide. So here we've done exactly that. That input voltage, that voltage divider connected to the input of my buffer could not be allowed to supply any current, right? If I just connect it, right? If I had my voltage divider set like this, and I want to obtain some voltage V, well, I'm just going to call it VB in this case. Well, and then I went and connected a load to this RL. Oops. RL. Now my voltage with RL, VB is, let me say here that VB with RL attached is not equal to what VB was initially. Let's say initially. Okay. You might say, well, I can just adjust my voltage divider here. You know, I can change the value of this resistor to get the voltage I want with this load attached. Well, what happens if this load is variable? Right? What if it changes dependent on what's happening in the circuit? Right? Well, now this becomes a problem. I have no means of accommodating those that changing resistance without also continually changing the voltage divider here as well. Whereas in this circuit, my resistor here can be a variable resistance, my load resistance, and still my op-amp, my unity gain buffer, will make sure it supplies whatever current is necessary to provide the current requirements of the load within the capabilities of the op amp. Clearly, we can't provide 100 amps from the output of this op amp if it's not rated to supply that type of current. So there are some limitations. So again, a unity gain buffer is simply an op amp that has the output tied directly back to the input. So the gain here is 1, but the output is able to supply current that may not otherwise be able to be supplied by the input circuit. Okay, so it's buffering the input. It's isolating what's connected to the input from the output. Okay, so again, this all being a result of this property of this these non-inverting buffers having an input resistance. It's infinite. Okay, quite a beneficial property. Let's look at the input resistance of an inverting amplifier. Okay, so going back to our inverting amplifier configuration we looked at in a previous lecture, here we had the non-inverting terminal connected to ground. We had the input fed in to the inverting terminal through a input resistance. We had a resistor in the feedback path from output to inverting input, which we've called R2, but sometimes called RF. Okay, and again, we can kind of treat this circuit like a black box and assess what the input resistance is here by applying a test voltage and measuring the current flow into the input, allowing us to calculate the input resistance. Okay, let me note here that my voltage at my positive terminal is equal to 0, and that both of those terminals are going to be equal in voltage because of the infinite gain properties of my op amp. So here I have my voltage of my non-inverting terminal is 0, and that's also going to be equal to the voltage of my inverting terminal, right? And this is in fact what we call a virtual ground at this point, because its voltage is 0. Okay, so then I can, if I know the voltage at one side of the resistor here is 0, so here I'm at, let me maybe zoom in here for a second, here I'm at 0 volts here, so the voltage across this resistor, I'm just going to call it VR1, is simply equal to the voltage at the input. So the voltage across the resistor VR1 is going to be equal to the voltage applied to one side of the resistor minus the voltage on the other side, which is 0 volts. So therefore VR1 is simply equal to my input voltage Vx. Okay, so Ix, the current flowing into the input, and the current flowing through R1 must be equal to VR1 divided by R1. I just said that the voltage across R1 is equal to Vx. So that's Vx divided by R1. Rearranging this, I see that R1 is therefore equal to Vx over Ix. And now this equation should look familiar. This is the equation that we use to calculate the input resistance. Okay, so the input resistance here is equal to Ix Vx, Ix divided by Vx, Vx divided by Ix, and in this particular case we see that that resistance, input resistance, is so my input resistance is equal to R1, which is not nearly as ideal as the non-inverting configuration. Okay, and so your first thought might be, well, we can make it as high as we want by increasing the size of R1. We can just use a really large resistor. But let's remind ourselves that the gain of this inverting amplifier is equal to the negative of R2 divided by R1. Okay, and let's just focus just on the magnitude of the gain. Okay, so R2 over R1, and we said that R1 is also the input resistance. So thinking about the gain relative to R1, I see that just through a simple rearranging of this formula, I see that I can't have both high gain and high input resistance, right? If the input resistance, if the gain is high, the input resistance is going to be low. If the input resistance is high, the gain is going to be low. Okay, so they are inversely proportional here. So cannot have high gain, AV, and high input resistance. Okay, so it's one or the other. We can probably find some middle ground where we have a moderate amount of gain and a moderate amount of input resistance, but if you're really looking to approximate kind of our ideal amplifiers with a very high or infinite resistance, then you may want to be looking at our non-inverting amplifier where the gain are near infinite, or again for a real op amp in the mega or giga ohms, as compared to an inverting configuration where the input resistance is exactly equal to that input resistance, that resistor R1 that is used to set the gain of that inverting amplifier. Okay. Let's talk, just because it only is a brief discussion, let's talk right now about output resistance. Okay, so let's look at our op amp again. Let me do a little bit and expand it. Actually, let me kind of show the internals of our op amp. So if we're assuming our op amp can be represented by the model of the output of a voltage amplifier, so we stick this inside an op amp here, body, right? This is what our output stage can be modeled as, right? Where the gain is the open loop gain of the op amp times the differential voltage, the voltage difference between the non-inverting and the inverting terminal. Okay, so we can assess the output resistance here just like we do the input resistance, right, by applying a test voltage Vx and monitoring the current that flows into that input, and this will allow us to assess the output resistance of an op amp. Now you might say, well, what about the any resistance that's connected in the feedback path here, right? We well, I guess maybe the feedback path here is going this way to provide negative feedback. So if this is my feedback looking into the output, in fact it's very easy to ignore any current that's flowing through that feedback path relative to the current that's flowing into the output here. So this current here is this current is going to be approximately equal to the test current Ix, because the resistance of this feedback path is much larger than the resistance, the output resistance of the op amp itself. Okay, so resistance in feedback is much larger than RO. So there. So therefore, we're going to ignore the resistance in the feedback path, right? Whatever that resistance is here. Well, let's just call it resistance in the feedback path here, whatever that is. Okay, so let me make my ground connection here of my op amp. So now if I've assumed that this current that's supplied by my test voltage Ix is flowing only into the input, and I can neglect the portion of it that's flowing through the feedback path, then I can say that Vx is equal to Ix times the output resistance, because, and again you might say, well, what about this this voltage source that's controlled by the differential gain? Well, if you remember Thevenin's theorem, Thevenin says that we short out any voltage sources when we're assessing resistance. So that voltage source is shorted out, so then the voltage that's applied here as Vx, that voltage is going to appear directly across Rx, our output resistance. So therefore our Ohm's law equation here applies. So rearranging that equation, in terms of a resistance. Vx divided by Ix, just like we did on the input side, will give us a resistance. In this case, it's equal to our output resistance. Again, just to reiterate here, we're ignoring any resistance in the feedback path. Okay, and often we assume that the output resistance is small enough to be negligible, and we treat it as though it's 0. We look at a real op amp, we'll see it's not in fact 0, but it often is low, and it will vary from op amp to op amp. Okay, so that's input and output resistance of op amps, input resistance of op amps in both inverting and non-inverting configurations. Output resistance is really the same regardless of the configuration and regardless of the feedback path. Its output resistance is purely the resistance of the output of the op amp itself, and assuming that that output resistance is very low, we can normally safely assume that output resistance to be 0 or very close to 0. Next class we'll have a look at another op amp configuration yet again, and that will be a differential amplifier.